All right, we're going to move on now to why are limits so annoying? I hate them. So as we've seen above, there's a lot of issues with discontinuities that can show up in a lot of places, and in order to figure out where the discontinuities are, we need to be able to calculate limits pretty easily. So it would be nice to have a better method of calculating these limits. We talked about limits in section 2.2. Now we're going to talk about some of the better techniques for how to actually calculate them. And in section 2.3, the textbook proves what are called the limit laws. And you can read the section if you want the full details, but basically the conclusions are this: if you have a limit that you know, so suppose limit as x approaches p of f of x is equal to L, some number, and for some other function you know that that limit at that same point is equal to something else, then if you add those functions or subtract them or multiply them, then the limit at that point of those added, subtracted, and multiplied functions will just be the limits added, subtracted, or multiplied. So a quick example of this is, suppose you had some function and the limit as x approaches 4 of f of x was equal to 6, and you had some other function where as you approached 4, maybe that function g of x was equal to 2. And then the limit as x approaches 4 of f of x plus g of x, a new function where you're adding those two original functions together, well, since you're going to that same point, you're just going to add those two limits to get 8. And the limit as x approaches 4 of f of x times g of x, well, that'll just give you 12 because you're just multiplying the 6 times the 2. That's all that this is saying. And the reverse also happens, that if you have a function that's maybe more complicated, but you can break it up into smaller pieces where you can calculate each of those limits, then you can use those smaller pieces to calculate the limits. The one caveat, of course, is that you can't divide by 0. Okay, so if you had, say, the limit of g was 0, then the limit as x approaches 4 of f of x over g of x, that would be giving you 6 over 0, which would be undefined. So here, both of these original limits would be defined, but that next limit would not, because you'd be trying to divide by 0. And how can we use this? Well, there's a couple limits that are actually pretty easy to calculate. So the function y equals x, or f of x equals x, that's just a straight diagonal line where your x value is always the same as your y value. If this is 2, then that's also 2. And in this particular case, we know that it's a single unbroken line, and the x value we plug in is the same as the y value we get out. We know that's always going to be the case. So what that means is that the limit as x approaches p of the function x, this is where f of x is equal to x, it'll always just give us p. Whatever you're plugging in, you're going to get out as your y value. And then similarly for the constant functions, if you have a constant function that's something like, I don't know, this is f of x equals 4. There's my x coordinate, y. It's just, again, a single unbroken line, but it's horizontal. And here, no matter what you plug in for x, your y value is always equal to 4. So that limit will always just be c, whatever that constant value is. And if you look at a polynomial, something like this, well, x cubed is just x times x times x. You're taking a function where you know the limit and you're just multiplying it by itself a couple times. We still know that limit according to the limit laws. And the same thing goes for all of these. You have some numbers in there, well, those are the same as just constant functions. So let me show you real quick how we would break this down in example 3 to calculate this limit. And this is going to look rather long and tiresome, and soon we will be making it a little bit easier. So here's the idea. If I have the limit of this whole thing, I can break that up into a bunch of pieces. So the limit as x approaches 3 of x cubed plus the limit as x approaches 3 of 2x squared plus the limit as x approaches 3, sorry, that should not be a plus, that should be a minus limit as x approaches 3 of 5x plus the limit as x approaches 3 of 7. And what is the limit as x approaches 3 of x cubed? Well, that's the same thing as the limit as x approaches 3 of x times the limit as x approaches 3 of x times the limit as x approaches 3 of x. What I'm saying is I've got x times x times x in my x cubed, so I can take the limits of each of those x's individually. And then the 2x squared, that's the limit as x approaches 3 of 2 times the limit as x approaches 3 of x times the limit as x approaches 3 of x minus the limit as x approaches 3 of 5 times the limit as x approaches 3 of x. Now this one is actually easier. What is the limit as x approaches 3 of 7? Well, the constant function 7, I'm not thinking of this as a number now, I'm thinking of it as a function 7. That's always going to be 7. This is always going to be 7 all the time. So that is just going to turn into a 7. And we're going to do the same thing with all these. What's the limit as x approaches 3 of x? Well, as we set up here for this particular function, f of x equals x, what you're getting out as your limit is just the p-value of the thing you're going to. So this one will equal 3, and that one will equal 3, and that one will equal 3. Now the limit as x approaches 3 of 2, this is now a constant function. It's like this. That's going to give me 2. Then I'll get a 3 here and a 3 there, just like I got those 3's. Minus, this will give me a 5, that'll give me a 3, plus 7, this is 27 plus 18 minus 15 plus 7, comes out to being 37. And there's an even easier way of understanding what's going on here. If you let f of x equal x cubed plus 2x squared minus 5x plus 7, to find the limit as x approaches 3 of that, of f of x, it's just going to be f of 3. So I'm plugging in 3 for x. That's 3 cubed plus 2 times 3 squared minus 5 times 3 plus 7, which, as we saw above, also gives me 37. So breaking it up into all these different pieces is the same thing as just plugging in 3 for x. So go ahead and use that exact same reasoning to see if you can figure out, without graphing or anything, what the exercise, or what the value is for exercise 4. Calculate that limit for exercise 4. Go ahead and pause the video now and try to work on that on your own. Okay. If I wanted to do this the long way, the way I did it above, I would say, well, this is equal to the limit as x approaches 4 of x, of that first thing, plus the limit as x approaches 4 of 7, divided by the limit as x approaches 4 of x, times the limit as x approaches 4 of x again, because I've got an x squared, minus the limit as x approaches 4 of 1. Of course, this will just give me 4. That will just give me 7. This will give me a 4 times 4. And this will just give me 1. This comes out to being 11 divided by 15. And that's the answer for exercise 4. If you recognize that we weren't going to be having any issues here and you just plugged in 4 there and 4 there, you would get the same thing. And that's correct. A quick note is that this is actually much more difficult. And the reason is, if you try to plug in 1, you'd be getting 1 plus 7 on top, and then 1 squared minus 1 on the bottom. That's 8 divided by 0, but you can't divide by 0. So remember earlier I said the only issue we have with these limit laws is when you're dividing by 0. And in particular, you can't do that. So in this case, we were fine in exercise 4 because the thing we were plugging in did not give us a 0 on the bottom. But if it did, it's more complicated, and we'll talk about that later. Last thing I want to mention is just a quick remark that limits, I just said, something to like the x squared power is easy to calculate. And when you're under a square root or a cube root or something like that, these are also things to a power, they're just fractional powers. And it turns out that limits for these are also very easy in the same way that they were for polynomials. You just have to be careful about whether or not the function is defined. So here, the limit as x approaches 3 of the cube root of x to the 4th over 2 minus 3. This is the same thing as the cube root of the limit as x approaches 4 of x to the 4th divided by, or let's say x to the 4th over 2, keep that easy, minus the limit as x approaches 4 of 3. And I'm not going to go ahead and write this out 4 times and divide it by 2. I'm just going to go ahead and plug in 4 here. 4 raised to the 4th power, so this is the cube root of 4 raised to the 4th power, divided by 2 minus 3. When I plug that into my calculator, I get the cube root of 125. This is the same thing as 125 to the 1/3 power, which I can either plug into my calculator or know that the cube root of 125 is 5, because 5 times 5 times 5 equals 125. On the other hand, if I have the limit as x approaches 4 of x squared minus 20, square root of x squared minus 25, when I try just substituting in 4 here, I get the square root of 16 minus 25, which is the square root of negative 9, which does not exist. Okay, so this limit does not exist. And the reason is because we can't divide by a square root. Or sorry, we cannot take the square root of a negative number. Unless we are allowed to have complex numbers, which you probably learned about in pre-calculus. But for calculus, for Calc 1, our focus is only really on real numbers. So in this case, we would say that is not defined. And we can summarize this whole thing in what's called the direct substitution property. And basically this says that if a function is a polynomial or a rational function, then the limit at a certain point is exactly the same thing as just plugging in the number. Okay? And in fact, this is going to be true for functions other than polynomials or rational functions. Our step 1, I guess, for all limits is you first just try plugging in the number. And if it is defined, then that is your limit. And this is true for this is true for all functions that are very straightforward functions like these. It can get a little more confusing if you have piecewise functions, and we'll talk more about those later.